Well, I guess we're ready. Can everyone hear me okay? Excellent. I want to do a quick check here just to make sure that the fonts on my demos are big enough. Is that font readable in the back row? And the person needs to raise their hand needs to be the old graybeard with glasses. Yeah. Okay, how about here? Is that visible? I mean, aside from the fact that it's light green on white. Excellent. So welcome. My name is Guy Royse, and this is an introduction to WebAssembly. Quick show of hands. How many of you would be willing to raise your hand, would not be willing to raise your hand if I asked you to raise your hand? I knew I liked you. So, yeah, let's talk about WebAssembly. This is me. I'm a developer advocate with Redis Labs. Today is my first day at Redis Labs. So hooray for me. And so if you ask me questions about Redis, I can't answer them yet. But I've had this talk in the works for a while, so I can answer WebAssembly questions. If you want to follow me on Twitter, I'm at Guy Royse. I have the domain name guy.dev, which is perhaps the most awesome domain name I have ever owned in my life. And so you can check out my blog that I don't update on guy.dev. And I've got a code.guy.dev. I'll take you to my GitHub repo. All the code that we'll show today will be out on GitHub for you to check out. So, but yeah, that's what I do. And I'm a fan of WebAssembly. I don't purport to be an expert on WebAssembly, but it's something I think is really cool, has a lot of potential. And so I've dove into it and have been putting together this talk and just playing with it. And you know, the first question you have to ask with WebAssembly is, what is WebAssembly? So I asked my computer wife, Karen, the SpongeBob Karen, not the internet meme Karen, and she said it was 50% web and 50% assembly. And it's one of those things where it's trying to be funny, but it's actually really true too, because it is assembly language for the web. But at its heart, it's really a solution to a problem. And that problem is JavaScript. What the hell, JavaScript? Now, before I proceed to pick on JavaScript, I want to say that I actually like JavaScript. I like JavaScript unironically. I run a JavaScript user group. I enjoy programming in this language. It's got some weird corners. It's a little challenged at times. But you know, overall, I think it's a pretty a reasonable language. But some of the corners are weird, like this first one. Array is equal to not array. Well, that's true. Okay. Not a number, triple equals not a number, that's false. But they're the same thing, right? A number.min value is greater than 0. That's true. I don't think my bank agrees with JavaScript. My favorite is parse-int firetruck. That returns not a number. This is probably the most reasonable line of code in these examples here, because I'm pretty sure firetrucks aren't numbers. However, if you say parse-int firetruck, comma 16, well, that's 15. And what's happening here is that parse-int is looking, you give it that 16, you're saying parse hexadecimal. And F is a valid hexadecimal digit, it's 15. And then it sees the I and says, well, that's not a valid hexadecimal digit, and so it gives up. It says, I'll just stop here. Close enough. Now, you might be wondering why I picked the word firetruck. It's kind of random. Well, it's sort of a hidden expression of how I feel about some of these weird corners of JavaScript. My son, who's 18 now, but at the time he was about 10, he told me this joke. He said, Dad, I'm thinking of a word that starts with F and it ends in UCK. I'm like, yeah. He's like, yeah, fire truck. Like, good joke, son. I think my favorite one here is the console.log.call.call.call.call.call ad nauseum. And I think this is interesting because every function in JavaScript has a call function and an apply function on it. And call calls that function with specific values for this. And we all love the values of this in JavaScript because it's so easy to understand. But call itself is a function, and so it has a reference to itself. And so you can just chain this call as often as you want. And it's just sort of absurd looking, but perfectly valid. And then there's the ever wonderful math.min is greater than math.max. I don't know how that works. I don't get it. Maybe it's like an overflow, you're going around the horn. I don't know. So now it's easy to pick on JavaScript, right? We've all done it. But I'm going to say in JavaScript's defense, Brendan Eich wrote it in 10 days. I have not written a language in 10 days. So we can forgive it having some weird corners. But there's another aspect of why did he write that language in 10 days? It was because they were competing with Microsoft at the time, and Netscape's trying to get a browser out and getting a language for the client side, and Microsoft had a competing language, and that was VB script. And so we can complain and moan about JavaScript, but can you imagine a world? It's horrid, isn't it? So I say count your blessings and be grateful for JavaScript. JavaScript, though, a lot of people just don't like it as a language, and that's great. I mean, if you want to do front-end development, you can choose another language, as long as it's JavaScript. And I know what you're thinking, well, I could do TypeScript, or I could do Elm, or some other language that transpiles to JavaScript. But it's still JavaScript under the covers, and your errors still come out in JavaScript. And so you have to really understand JavaScript to understand why TypeScript isn't doing the things that you expect it to do. And it's kind of like, well, we made up a word to describe this process. You're not compiling it, you're transpiling it. The fact that we had to make up a word to describe the act of taking something and turning it into JavaScript kind of is a hint as to what we're doing here. And so we're not really escaping JavaScript, we're sort of covering it up. We're putting lipstick on a pig. And so yeah, you're kind of stuck with JavaScript. But there's actually a deeper problem with JavaScript. And some of it's been addressed by V8. But you have to download that JavaScript file. And it's text. Now you can compress that and you can minify that. And that can help with the download size. And so that's not a huge problem. But then you have to take that text file and you have to parse it into tokens. You have to find all of the syntactic tokens. And you take those tokens and you have to build an AST. You have to parse that out and create that abstract syntax tree. And then you can actually execute it. And you have to do this with these JavaScript files all the time. This is a slow process. This is the nature of an interpreted language. Now, I know that V8 actually does do compilation of the JavaScript under the covers, and we've gotten a lot of performance improvements out of it. But this is sort of where JavaScript began. And it's still a process that has to happen the first time you download that file. But what if you could compile code for your browser instead? What if you could write it in, say, C++? Because who doesn't want to build a website with C++? Do you like memory leaks? You'll love memory leaks in the browser. But it'd actually be pretty cool if you could compile code for the browser because, well, it'd be compiled. You wouldn't have to tokenize that and parse it because that's what compilers do. And so that would have already happened. And you'd be freed from having to use just JavaScript. You could use other languages like C++ or Rust or Go. And or other languages as they're coming on board with WebAssembly. That'd be pretty cool. And that's what WebAssembly is. That's one of the that's the problem. I think it's really the key problem WebAssembly is solving. It does address performance concerns. You can get more performance out of it. At least you will be able to, I think, when it's fully mature. But I think its number one feature is just that it frees us from JavaScript to use other languages to build our front-end applications. So I'm going to dive into how the WebAssembly, how it works at a very low level. And to do that, I'm going to explain a little bit about how microprocessors work. And so, quick show of hands, how many of you have programmed in assembly language before? It's always more in Europe. Good on you. How many have been paid to do it? Like 3. So I have not been paid to program in assembly language either, other than the stuff that I've done for this talk. And that's sort of an anomaly. But I actually learned assembly language when I was in high school as part of a electronics curriculum. And so I'm in my late 40s, and I'm kind of on the young side for having done any assembly language. And so I felt like a little refresher might be worthwhile. So we know that microprocessors, they have a series of instructions you feed them. They're just patterns of bits. It's just 5 volts and 0 volts, or 3.3 volts and 0 volts, depending on your architecture, coming into that microprocessor. And one pattern says do this thing, another pattern says do this other thing, and we feed these patterns in. They're a series of instructions that make them do things. And they're just a bunch of bits here, which is very easy to read, and everyone loves to program in. And so one of the early things that everyone decided to do is they said, this binary stuff sucks. We could do our code, our machine instructions in hex. That'd be a little easier to read for a human at least. But what if we created sort of a text file, a mnemonic that mapped to these instructions? And so instead of saying 101 and then a bunch of zeros, we could say LDY and then $00, meaning load the value of 0 onto the Y register on a 6502 microprocessor. And so this is an example of what the binary on the left would look like. Sorry, my little pointer broke before I did the talk, so I can't point at it. And my mouse doesn't want to cooperate either. But on the left here in green, we have the binary. On the far right in purple, we have the assembly language. And you can see the assembly language is a lot easier to read. It's still not easy to read, but it's a vast improvement. And everyone was pretty happy with using assembly, given where they had come from. Except one person. This is a fun little story I found. Von Neumann had been using grad students to be assemblers. So you'd write assembly language on paper, and then they would turn it into binary and put it into the computer in the mid-'70s. And grad students, being the lazy creatures that they are, decided to write an assembler. And so they could just type. So now this is just a typing exercise and not a assembly exercise. And when von Neumann found out they were doing that, he was very angry and said, "It is a waste of a valuable scientific computing instrument to use it to do clerical work." Now, I think that's hysterical. What is your job? Everything I've done in my entire career has been clerical work. That's like all we use computers for now. It's even worse than that. We're using it for obligatory cat videos on the internet, right? Von Neumann is probably rolling in his grave. I've got this valuable scientific computing instrument right here, and I just check to see what my mom says on Facebook. But he would be proud of me because the code that I showed you was actually the first assembly language code I ever wrote. I actually wrote it by paper, on paper, and then assembled it by hand and then put it into a circuit board with a 6502 microprocessor on it. And so this is the code I've been using this example here is code I actually wrote back in the late 80s. So that he at least has that. Eventually, everyone decided assembly language is kind of a pain. Part of the reason being, I have to learn a different machine code and therefore a different assembly for every microprocessor type I work on. So if you're working on a Motorola processor, it's got one instruction set. If you're working on an Intel processor, it's got a different instruction set. And so we came up with higher level languages like C and C++ that we could then compile as opposed to assemble. And so in an assembly language, each instruction there, each of these symbols corresponds to a byte. In a compiler, that's not true. We actually figure out what those bytes should be, and we can do it based on the different microprocessors. So I could write a program in C once and compile it for lots of platforms. And this was great. I could write my C++ code, it'd run on my 6502. But it turns out there's a lot of microprocessors. And so if you've written some software, you could write it for one processor, and you got to compile it for all these different machines. And as the number of processors expanded, you would tend to compile for the lowest common denominator. So if you're on an x86 architecture, you'd compile your code for the 8386, and then it would work on the 486, and so you'd be like, that's good enough for selling it on the market. So you couldn't take full advantage. And we solved this problem using the solution we always do, in software, which is we added another layer of abstraction. What if we created a virtual microprocessor? Then we could compile our code to that virtual microprocessor, and then that virtual microprocessor could interpret the bytecode for this particular processor we're on. And so that's how it works. So what was now over here on the left was C code is now Java code. And you can tell it's Java code because if you look closely at the bytes on the screen there, you can see the first 4 bytes say Cafe Babe, which every Java class file starts with. And then it would run on that virtual machine, which would then map to the physical hardware you had on your machine. And you could actually get a lot of value out of this because you could compile that bytecode to the actual microprocessor that's in the machine as opposed to a lowest common denominator processor. WebAssembly is exactly the same idea for the browser. So instead of having a virtual microprocessor that's running on my computer, I've got a virtual microprocessor, the WebAssembly virtual machine, running in a web browser. So we've got our code, we've got WebAssembly bytecode, that bytecode runs on that virtual machine, and it's supported by all the major browsers. You'll notice here in this picture, I've got all 4 of the browser icons. That is Edge, not Internet Explorer. It will not work on Internet Explorer. Don't even try it, please, for the love of God. Is anyone, yeah, I was going to say, is anyone still using Internet Explorer, but I know the answer to that question. Insurance companies are still using Internet Explorer. But it supports Chrome, Edge, Firefox, Safari. They all support WebAssembly. And the mobile versions as well. So these will work on your mobile browsers on your phone. So that's pretty cool. So let's get down a little more detailed into how the WebAssembly works in the browser. So on the left here, we've got our CSS, HTML, and JavaScript in our browser space, right? And these are all files we download off of a web server. The browser's using them. And this is sort of the classic trifecta that you use for front-end development, right? We've got a web page, we've got something to make it look pretty, and we've got some JavaScript to make it do some stuff. And then JavaScript to manipulate that DOM. It's very familiar territory. WebAssembly is just another file that we download from the web server. So a WebAssembly module is a binary. It's a .wasm file. We download it. We download it with JavaScript code. And then we can instantiate a WebAssembly module. So this little code in the box here, and we'll have a better sample in a bit. It instantiates that WebAssembly module. And then the WebAssembly module is essentially a bag of functions that JavaScript can call. But when you instantiate it, you can also give it a bag of functions for it to call you back on. And so WebAssembly can call JavaScript, JavaScript can call WebAssembly. You will note that I do not have an arrow between the WebAssembly and the HTML. That's because WebAssembly doesn't manipulate the DOM. It doesn't know about the DOM. It knows how to talk to JavaScript functions that you give it. And that's all it knows. If you want to go out and use WebAssembly to manipulate the DOM, you're going to have to call a JavaScript function to do it for you. If you want to go out and fetch a resource from the internet, you'll have to call a JavaScript function to do that for you. So WebAssembly is version 1.0. It doesn't know how to do those things yet. There are plans to incorporate those things. It's a hard problem. So I'm going to start diving into some code here. I'm going to use 2 languages. We got the WebAssembly. For the WebAssembly stuff, I'm going to use the WebAssembly Text Format. This is the assembly language that corresponds to the WebAssembly bytecode. So every operand in there is going to be a byte, or maybe 2 bytes, I'm not sure, but it's going to translate directly to the bytes in the WebAssembly module. And I'm going to use JavaScript. Now, I'm going to say up front, I don't recommend using WebAssembly Text Format to build production code because it's just too low level. This is more to understand how it works. If you want to build production code with WebAssembly, I'd recommend Rust or Go or C++. So here's a simple WebAssembly module. You can see here it's an add function. And WebAssembly is stack-based. So because it's a virtual microprocessor, it doesn't actually have the same sort of limitations that a physical one would have. And so you don't have registers, you just have a stack. And so what this means is that instead of storing something on register and storing something on another register and then calling add to add those 2 registers together, you can just push 2 things on the stack and add them together. So it looks like this. So in here, we're going to get $A, which is a number. That call to get local pushes that onto the stack. So now we have 5 on the stack. When we call get local B in our add function, it's going to push the B, push the number 10 onto the stack in this case. And now we've got 2 things on the stack. Then when we call add, right down here, it will pop both of those, the 2 elements off the stack, add them together, and then push the answer onto the stack. Then we're at the end of the function. We should have 1 and only 1 item on the stack. That's the return value. So this little add function adds 2 numbers together. Obviously, it's called add. And so that's a real simple WebAssembly module. From the JavaScript side, we can instantiate modules. There's 2 ways to do it. There's the OK way and the way better way. The OK way is slower, but more reliable. The way better way is faster. By reliable, I mean when I first did my samples, the OK way worked on Safari, but the way better way didn't work on Safari. I'd like to hope that Safari's fixed that by now, but in my samples, I'm still using the safer way, right? The key thing here is that you fetch that WebAssembly module, and then you're going to get a bunch of bytes back, and then you can use those bytes to instantiate it. And so here we're seeing up top, we got WebAssembly.instantiate, pass in those bytes. In the case of WebAssembly.instantiate streaming, it's going to start interpreting those things as they are streamed down. So it's not waiting to download everything before it does the next step. And so that's a little more performant. Either will work. The scales I've been working at, it hasn't mattered. Once you have that module, it's got an instance. The instance has exports, and the exports has all your functions. And so here I'm just calling add, which is the add function we had in the previous example. I'd mentioned that you can import and export functions. Exporting is pretty straightforward. There's just some functions that I can call on the thing that I get back when I instantiate. But you can also import. Here's a code sample for what exporting looks like on the WebAssembly side. So right here we've got 2 functions, or exporting and importing, sorry. 2 functions that we're exporting, 1 we're importing. And so you can see here we have this export keyword on the first line of each of those samples, which says, take that function $add and export it to JavaScript as add. Now I'm using the same word for both, but it wouldn't have to be that way. I could have called it foo and it wouldn't matter. For importing, we've got a couple of keywords in a doubly nested object that is passed in. And so we use this import keyword and map it to an internal name. And then we make an assumption about what the signature is on that function. JavaScript could lie to us and actually give us a function that takes 6 arguments, and we only know about 1. It'll still work because it's JavaScript. To get those imports in there, when you instantiate, you create this structure here, this let imports equals, it's a doubly nested object that's got just a bunch of things we want to import, in this case a function. We just pass that object in when we call instantiate. So that makes them available. There's also a start function, which I think is kind of neat. The start function allows you to, the start command allows you to specify one of your functions in your WebAssembly to be the startup. So when you instantiate that module, it immediately starts executing it. So that can be like a void main, or it could be an instantiation if you're thinking more object-oriented, more of a constructor. But it allows you to, for example, create a WebAssembly object that doesn't export any functions and it's all imports. And so it starts running, and the first thing it does is it says, okay, well, add a bunch of event listeners and start doing a bunch of stuff with the browser when this thing boots. One of the things you may have noticed in all my little samples here is that I've only been using numbers. And that's because WebAssembly doesn't know what a string is. And you're like, it doesn't know what a string is? This is awful. I don't want to use this. Well, what's a string? Right? In Java, a string is, well, it's kind of baked into the language. What's a string in C++ or C? Well, it's an array. Well, what's an array? WebAssembly doesn't know what any of these things are because it's a virtual microprocessor. Microprocessors don't know what strings are. They don't know what arrays are. They know what bytes are, and then they move them around. And so, depending on the language you're using, the definition of what a string is can vary. And so it makes sense that WebAssembly wouldn't define what a string is at this low level, because that's a language-specific implementation. If you were, for example, in Rust, strings are UTF-8 encoded. If you're doing some C++, there's other ways of encoding those strings. There's been several ways of encoding strings in C and C++ over the years. It started out as just a byte array, a char array. And so it's not making those assumptions. And so it doesn't provide that mechanism for you. However, WebAssembly also realizes that programming languages need to do things with things that are other than just numbers, right? It's not very useful if you're only using numbers. And so they have this idea of shared memory. You can think of this as a heap that JavaScript can see, because that sounds safe, right? Let's give JavaScript access, unprotected access to the heap. What could possibly go wrong? So you can create one of these shared memory modules, and you can define them inside of the WebAssembly, or you can define them inside of your JavaScript. And there's something that they can both see. So I can write more complex data out into my shared memory inside of my WebAssembly, and then JavaScript can see it, and vice versa. Now I have to write the code to make this work. But here's an example. Here we're importing our memory object, and then this sample WASM here has this data statement. It says, at location 0, i32 const 0, put the number 13. And so these are just like hard-coded data for when it's instantiated, when it's created. When it's started, you can also manipulate that by programmatically. And so here we're saying push the number 1 onto the stack, because at a location 1 in memory, I want to store something. And then push the next thing you push onto the stack is the value you want to store, and then you tell it to store it. So you're using that stack-based mechanism again. And so this pushes the number 23 into the second position, because we all want to write 1 byte of data with 3 lines of code. On the JavaScript side of things, we can see here that here we've instantiated the memory, all zeros. You can specify initial size. That's in page size is in 64 kilobytes. Then when we instantiate that WebAssembly module that we just looked at, it of course, the first thing it does is writes out a 13 and a 23 to memory. So now those are visible to JavaScript. We can pull that out of the memory buffer into an array, and we can literally just do JavaScript array manipulation to inspect and manipulate this memory structure. We can just set variables out there, rewrite them, do what we want. It's just basic array manipulation. And it turns out we can actually use this to store strings. WebAssembly doesn't know what a string is, but the WebAssembly text format has a context for storing strings in memory using these data statements. And so right here, I am storing a hello world in emoji. And you'll notice there's a /00. The /0 means we're not storing a character now, we're storing an actual number. And so it stores the wavy hand and the skin tone modifier to it. And then it stores the North-South America view of the world. And then it says store a literal 0 as the last byte. And so I have just shoved into memory here a null terminated string that JavaScript can use. And if any of you have done a lot of C or C++ in your careers, you're probably having flashbacks right about now. The null terminated string is back, baby. And then here in my hello world function, my hello function, I return the value 0, which is the location in that memory to find it. It's the address. It's a pointer. So we're returning a pointer to where that string is stored. And then in JavaScript, we can easily call that function, get that address, and take that memory buffer, turn it into an array, and just slice out the area we want, look for the 0, and then decode that to a JavaScript string. And JavaScript stores strings as UTF-16 encoded, and so now you have this string in JavaScript. So a lot of code just for a string, but that's what you do in WebAssembly today. There's a lot of other capabilities that I haven't talked about, but we may see in the code demo here. We got local variables in case the stack's not enough. You can create local variables you can make use of. You can also create globals. They're sort of like shared memory, but they're just a single value that JavaScript and WebAssembly can both see. And you can use them just as globals internally, just like you would in any other. You could abuse them internally like you would in any programming language. There's this S expression syntax, which I've been using all over the place, that allows the code to look a little lispy. And then we've got tables. And tables are for, like the virtual tables, the vtables you would have are for function pointers. They allow you to dynamically bind functions, which I don't have any examples of other than right here. But if you're building, say, a C++ compiler for WebAssembly, you have to have that capability so that you can support polymorphism. And so it's sort of like data statements, but for functions. If you want to start playing with this and not do it at the lowest level, the 3 languages that are sort of the go-to right now are C++, which has a very complex toolchain. There's Rust, which has a really easy toolchain. And there's Go, which I haven't really looked at yet. I don't know Go very well. I know Go has great WebAssembly support, but I haven't explored it yet. So you're welcome to. Rust is where I've done the most experimentation. And I found using Rust to generate WebAssembly modules is actually pretty straightforward. And I'll be demoing that here in just a moment. Also, there's this site, Awesome WASM Languages, that's got sort of a list of languages that are doing different things with WebAssembly. There's a Python WebAssembly interpreter that is sort of like a WebAssembly virtual machine, but written in Python. I saw a Java one where you can use annotations in your Java functions to say this is exported as WebAssembly, and it would transpile your Java bytecode to WebAssembly bytecode. So there's a bunch of interesting stuff out there. Go check it out. So let's do a demo. Who wants to see me live code and follow my ass? Everybody! All right. Okay. So I'm going to do FizzBuzz. And I'm going to use Jasmine just because it's quick and dirty and easy, and I know it really well. And because strings are hard, I'm not going to return fizz and buzz and FizzBuzz. I'm going to return -1 for fizz, -2 for buzz, and -3 for FizzBuzz. And we'll do this as far as, if we get low on time, I may cut this a little bit short. But let's go ahead and start by writing a test. You can just describe FizzBuzz. I also want to show you this here. I have a WASM helper. This is just a little function I wrote to return the WebAssembly module, the exports specifically. So FizzBuzz. So we're going to describe FizzBuzz. And the first thing we're going to need to do is instantiate a WebAssembly module. So we need an async done. Since instantiating is asynchronous, we need to use an async function. And then we have to call that done function when we're done. So we'll say this.subject. This.subject equals await load WASM. That's the function that I just showed you in the other file. And we're going to say fizzbuzz.wasm. There we go. And then we needed to do a thing. It, not instance of, returns the number it is given. So the simplest thing we can do with FizzBuzz is expect this.subject.fizzbuzz, when it's given a 1, to be a 1. It's a very sophisticated test. So let's go ahead and get our web server going. Got this little Python script here to do that. And it should be at port 8000. If I reload this, it should give us a timeout error in 5 seconds. Yes. It's timing out because it's trying to load the fizzbuzz.wasm and it doesn't exist. So we need to create a WASM file. So let's do that. Look down here, new file, FizzBuzz.wat. Okay, so module, and we're going to export FizzBuzz, and that's going to be a func named $FizzBuzz. So that's our little export statement. We'll define our FizzBuzz function. It takes one parameter named $num, and it's a 32-bit integer. It returns a 32-bit integer. All right, makes sense so far? And we want to return a hard-coded 1. So we're going to say, take the constant value of 1, push it on the stack, and then return. So we'll save that. So now how do we assemble this? Well, there's two ways we can do that. One is Visual Studio Code has a plugin that will allow me to save as WebAssembly binary file. If I right-click, it'll ask me for a file name. I hit save, and it says unexpected error. Oh, result, not results. There we go. Try that again. Save. Yes, replace it. And I think that worked. Let's take a look. So now we've got this WASM file here. Now we can't open this WASM file because it's binary, right? It's just a binary file. But the plugin I'm using for Visual Studio Code actually will disassemble it and hand it back to us, which is kind of cool. There's another way we can do this. I can find my terminal. There we go. Oh, I forgot to background this guy. Background. So if we look here, we see our FizzBuzz.wasm is a whopping 72 bytes right here. So nice and tight. We do a hex dump. You can see that FizzBuzz.wasm, that's the actual generated bytecode. But there's a tool called the WebAssembly Binary Toolkit, or WABIT, which is funny. And WABIT has a tool called WAT to WASM, which takes a WAT file and converts it into a WASM file. And so WAT to WASM, FizzBuzz.wat, will then spit out the WASM file. So that's the other way you can do the compilation. I have actually wrapped that up into a WAT build shell script to do that for me. But regardless, we've now assembled this thing like 4 or 5 times. Let's see if it actually works. Hey, it passes. All right. Cool. Let's write another test. It's actual real stuff. It's not just vaporware. So we need to return other numbers. So it returns other numbers it is given. It shouldn't just always return 1. It needs to return other things. So let's give it a 2 and expect a 2 back. We refresh that. We can see that it fails for the expected reason. Expected 1 to be 2. That's definitely a failure condition. So let's make this a little smarter. And instead of saying i32 const, right, we'll delete that and say local.get. This will get the local value. You can also do get underscore local. They're synonymous. $num. And that will put whatever was passed in on the stack. And so now instead of returning a hard-coded 1, it's going to be an echo function. And we can see that that clearly works. So what's the next thing in FizzBuzz? It returns -1 for multiples of 3. So if we give it a 3, we should get a -1 back. Now this is going to fail, right? Expecting 3 to be -1. So it's doing a good job of echoing. Let's go ahead and fix this. So now we need to do something a little more interesting. We got to get the number, and then we need to say if this number is 3, then return -1, otherwise return the number. So i32 const 3. So now we have the number and we have 3 on the stack. And we're going to say i32.eq. And what eq does is says if these numbers are the same, if the two numbers on the stack are equal, we'll pop them both, and then push down a true or a false, a 1 or a 0. And then we can use that in an if statement. So if will pop the stack and say if it's a 1, then do what's in here. And so we're going to say i32 const -1 and return. So that's one path. And then to echo the value back out, we need to actually return. We need to push something onto the stack. Otherwise, the stack is empty. Build it. And see, it indeed passes. I'm totally not flopping. Well, I mean, maybe I'm flopping, but my tests are passing. Let's make it a little bit smarter. And we'll, not -2, -1 for other multiples of 3, right? Let's pass in a 6. That's going to complain that 6 is not -1. And so we, instead of just saying is it equal to 3, we now need to do a modulus operation here. And to do that, we use i32.rem_u. Give me the remainder of the division of these two numbers as an unsigned number. And now we want to say equals z. So if it's equal to z equals 0, then do our condition. Otherwise, return the value.
You didn't type I32.
What's that?
You did not type I32. You typed 132.
Oh, thank you. Pair programming for the win. What I love about that is the fact that you were paying enough attention to follow it and find a mistake. It always makes you feel good. So thank you very much. And so, okay, that passes. Cool. Let's do the other multiples. And I'm going to cheat and write 2 tests here. I'm going to not be a TDD purist. For multiples of 5 and for other multiples of 5. And we'll pass in 5 and 10. And we'll expect that to be -2 and -2. And now we'll have 2 failing tests. And we need to do what every programmer does. I don't always reuse code, but when I do, I copy and paste. So here we're going to do modulus 5 and then return -2. So this is the easiest thing that will work. And indeed, it does work. This is why everyone is so tempted with copy and paste, isn't it, right? It's so easy and quick. And so there's some clear duplication here. So I'm going to write a little helper function to eliminate that. I'm going to write an is multiple of function. So let's do func is multiple. And this guy is going to take a parameter of num, which is i32, a parameter of divisor, which is i32, and a result that is an i32. And it's going to do basically these 4 lines of code, except instead of a constant of 3, we're going to get the divisor. So this gets the number, puts it on the stack, the divisor puts it on the stack, does the same thing, but it's parameterized now. And so in here, to then call that, we have to push the number and the divisor onto the stack. And so we didn't get rid of 4 lines of code like we'd hoped. We instead got rid of 2 lines of code and replaced them with 1. So got rid of a little bit of duplication here. Make sure that builds and passes. It does. So one quick thing I'm going to show you here too, and then I'm going to show you the Rust code, is the S expression syntax. So instead of constantly pushing things on the stacks, you can nest them in parentheses to make it a little more readable. So this line here does the innermost parentheses first, pushes the num on the stack, pushes the 5 on the stack, then the next thing up inside the parentheses is it does the call. So it's doing exactly the same thing, but it's just easier for humans to read. And so we could swap out a lot of code in here with this implementation here, but I'm just going to do the 1 just to show that it works. And see, our tests still pass. And so you could go through and clean up a whole bunch of code. And let's do the if statement. Then do that. We'll call return. That's not the typo I usually make for return. Usually it's ret run. And let's just do one-line ifs, because we all like one-line ifs, right? And then we could do 3 here, and -1. And then, just for consistency, there we go. So now that's a lot less vertical, a little more horizontal code, a little easier to read. I mean, I still wouldn't want to program in this on a daily basis, but there we go, and all the tests still pass. So let's take a quick look at the Rust code. So I've done an implementation of FizzBuzz and Rust here. Make it a little bit bigger there. And so here I'm using Rust matching. I'm using a tuple to do the 3 and 5 modulus operation, and then I'm just using true-false maps. But it's effectively the same thing as what we've just done, although complete. And I'm going to break it here on purpose just to show you so you can see it fail. So if it's a multiple of 3, it's going to return -10 instead. And I've got a little shell script here to build the Rust code. And I'm just using Rust C. I could have specified some of these in a cargo toml, but for a little one-line demo, just a single line of compilation in a shell script was easier. WebAssembly tends to spit out really big WASM files, and so this WASM GH will shrink them down. So let's go ahead and do /rust /rust build. Now if we look here, here's our fizzbuzz.rs.big.wasm. You can see it's 1.7 megabytes. That's actually pretty big for FizzBuzz. But if we look at the shrunk down version, it's 233 bytes. It's still not as tight as the other one that I wrote, but mine's also not finished. So let's swap out in our spec. Instead of bringing in FizzBuzz WASM, let's bring in fizzbuzz.rs.wasm. And you can see that the -1 case fails. If we fix the Rust, rebuild, and now it passes. So I've swapped out WebAssembly text format generated code for Rust code. I could have done the same thing with Go or C++. Rust was just the one that I knew the best. So, cool. Let's get back to the slides here. I've got 2 minutes. So a quick page of resources. WebAssembly.org has all the information on the bytecode. It's written from the point of view of someone who want to build a compiler, but you can use that to also figure out the WebAssembly text format. MDN's got great documentation for the JavaScript side of things. WebAssembly binary toolkit's the command line tool, WABIT. WebAssembly toolkit for VS Code is the plugin I use for Visual Studio Code. And then there's some other stuff here you can check out as well. If you want to check out the code for this, it's on my intro to WebAssembly. Slides are there too. I did a WASM FizzBuzz that actually returns strings. It took me about 3 days, and it's probably the most worthless thing I've ever been paid to do. I don't know, maybe not. It's up there. Top 5, definitely. But I did a full model view controller and everything. It's like totally over-engineered. But that's also out there. You can check it out as well. And so my name's Guy Royse, developer advocate with Redis Labs, first day. And thanks. I got like 1 minute. I could take like one question. Real quick question before the applause comes streaming in because I'm awesome. Yes, sir.
Is there any support for debugging?
The question is there any support for debugging? The answer is actually yes. And let me show you real quick. That was actually something I meant to show, but if we go into inspect here and look at the developer tools, you can see that, right? And go to my sources and see if I can find it here. And
Command P.
What's that?
Command P shortcut for finding by name.
Now, I know there is there. I've been able to look at it'll disassemble the code and you can step through it. I don't remember where it's at. But yeah, the answer is yes. I could show it afterwards if you want to see it. We can hunt for it. But you're able to actually set breakpoints within the WebAssembly and step through it and everything just like you would with JavaScript. So, cool. Great question. Thank you very much. You've been a wonderful audience.